Hey everyone! Did you know that in our galaxy around a staggering 1 to 3 stars are born every year? That's right, it's like a starry factory out there. And today we are diving into how this cosmic magic happens. So stick around because the birth of a star is a wild journey. Let's begin. Let's recap what we have learned about star formation in the previous video. First of all, it all starts in these massive molecular clouds, also known as stellar nurseries. These clouds are made up of gas and dust, and they can be thousands of times more massive than our Sun. Over time, gravity starts to pull the material inwards, and as this happens, the cloud begins to collapse and form clumps, which we call protostars. During this stage, the temperature rises and the protostar gathers more and more material from its surroundings. Eventually, the core gets hot enough to ignite nuclear fusion, which leads to the birth of a star. And then comes the big moment, when the temperature in the protostar's core reaches about 10 million degrees Celsius, the nuclear fusion kicks off. This process releases an immense amount of energy, and boom, a new star is born. This marks a key moment in the cosmic recipe as the star now begins to shine and influence its environment. It's like switching on a massive light bulb in the universe. The diagonal line in the HR diagram, remember the Hertzsprung-Russell diagram? Where stars of various masses first reach the main sequence and begin equilibrium hydrogen burning is called ZAMS, that is, the zero-age main sequence. Observations show that when a cloud fragments, more low-mass stars are formed relative to the massive ones. This means that the number of stars that form per unit area in the disk of a galaxy is mass-dependent. This functional dependence is known as the IMF, or the initial mass function. For decades, astronomers have worked on many such functional forms, one of which is shown here. This figure represents the number of main sequence stars found per unit area in the disk of the Milky Way per unit interval of log of mass in different mass intervals. The points are the observed data, while the curve represents the theoretical estimate. There are several interesting points to be noticed here. Observations suggest that the IMF at the massive end is bound around 100 solar masses. That is, there are hardly any stars more massive than about 100 times the mass of the Sun. Also, below around 0.1 solar masses, the IMF is quite uncertain and does not fall off as sharply as suggested by the models. In fact, according to the observations, the curve is quite flat in the low mass regime, and there may exist a lot of low mass stars and brown dwarfs, which we discussed in the previous video. As a massive star forms, the protostar will initially appear as an infrared source embedded inside a molecular cloud. With the temperature of the cloud rising, first the dust will vaporize, then the molecules will dissociate, and finally the star, which is on the main sequence, the gas immediately surrounding it will ionize, resulting in the creation of an H2 region inside an existing H1 region. But due to the high luminosity of stars, radiation pressure will begin to drive significant amounts of mass loss, which will disperse the remainder of the cloud. If several O and B stars form at the same time, it may happen that the mass which is not yet gravitationally bound to the slowly forming low-mass protostars is completely driven away, and therefore it will halt any further star formation. Groups of stars that are dominated by O and B type main sequence stars are known as OB associations. Studies of their behavior reveal that they cannot remain gravitationally bound to one another as permanent star clusters. Since we mentioned the infrared radiation, let's take a minute to understand what we see in different lights. Recall that the energy of photons is inversely proportional to their wavelength. The hot and massive O and B stars emit short wavelength UV radiation, while the bulk of the middle-aged stars are best observed in the optical. And as we discussed in a previous video, the cold hydrogen gas is studied using the 21 cm radio waves. Similarly, the dust, which is much colder than the stars, has no light of its own, but it absorbs the light of the stars in its vicinity and reflects them back. These recycled photons therefore lose a lot of their energy in the process and are observed at infrared wavelengths. The image here shows how the spectrum of a star changes when it is observed through the surrounding dust or intervening hydrogen clouds. And of course, the entire spectrum is redshifted because of the distance covered by the photons to reach the Earth. Essentially, this means that we see different components of an object when we observe it at different wavelengths. In a nutshell, the ultraviolet represents the most massive short-lived stars, while most of the other stars are best seen in visible light. Radio images reveal the gas, while the infrared represents the dust surrounding young stars and H2 regions. The X-rays that we have not mentioned so far are very high energy radiation which are used to observe very hot gas found in clusters of galaxies. By the way, did you know that X-ray observing techniques were first developed for astronomy and later used in the medical industry? At the cost of reiterating myself, here is another example of multi-wavelength observations of a few galaxies. As you can see, the red, green and blue in these images do not always coincide. The red, green and blue colors represent the dust from infrared, stars from near-infrared and very young stars from the far ultraviolet observations. These images therefore prove that not only do different wavelengths represent different components of a galaxy, but they often do not overlap with each other. So whether they are studying stars or galaxies, the modern-day astronomers heavily rely on multi-wavelength observations and analysis to explore all the components of an object and get a complete picture of its status. The discussion about the HR diagram so far may have given you the impression that the main sequence is a straight line, but that is not really true. Main sequence has a finite width, which is a consequence of a number of factors, some of which are observational errors, different chemical composition of the individual stars in a particular study, and varying stages of evolution in the main sequence itself. On the main sequence, the evolution of stars of different masses is not the same, mainly because their internal structure is different from each other. Let's begin with the low mass stars. Main sequence stars in the mass range of 0.3 to about 1.2 solar masses have radiative cores, while those with even lower masses have convective cores. But what does radiative and convective mean? Well, consider the example of water boiling on the stovetop, which adequately demonstrates the three different transport mechanisms for energy. When photons carry the energy to a surface and in the process get absorbed and re-emitted on the way, it is known as radiation. In our example, the radiation carries the heat energy from the stove to the pan. On the other hand, when energy is transferred by mass motion of a fluid, for instance, the mixing of water in the pan as the bottom layer begins to heat up, is known as convection. This mixing of layers of water transfers the energy from the lower part of the pan to the upper surface. The third mechanism is conduction, which is the energy transfer between two surfaces via direct contact when the two surfaces are at different temperatures. This process does not play an important role in most stars. So coming back to the low mass stars, notice that the main sequence stars in the mass range of 0.3 to 1.2 solar masses have radiative cores, while those with even lower masses have convective cores. Consider a star like our Sun, for instance. The temperature, luminosity and radius of the Sun have all increased steadily since it reached the main sequence about 5 billion years ago. As we discussed in an earlier video, this evolution occurs because the pp chain, which is converting hydrogen to helium in the core of the Sun, is responsible for increasing the mean molecular weight of its constituent gas particles. In accordance with the ideal gas law, unless the density or temperature of the core also increases, there will be insufficient gas pressure to support the overlying layers of the star. As a result, the core must be compressed. While the density of the core increases, gravitational potential energy is released, and as required by the virial theorem, half of it is radiated away and half of it goes into increasing the thermal energy, that is, the temperature of the gas. One of the consequences of this increase in temperature is that the core of the star, which is hot enough to undergo nuclear reactions, increases slightly during the main sequence phase of the evolution. In addition, since the pp chain nuclear reaction rate goes as temperature to the power 6, the increased temperature and density not just compensates for the decrease in the mass fraction of hydrogen, but the luminosity of the star slowly increases along with its radius and effective temperature. This process slowly depletes the hydrogen in the core of the Sun, therefore ending its hydrogen burning stage. But the core temperature at this point has increased so much that nuclear fusion of hydrogen continues in a thick shell surrounding the innermost core, primarily made up of helium. At this stage, the energy produced in the thick shell exceeds the energy that was produced in the core during the hydrogen burning phase. As a result, the luminosity continues to rise and some of it goes into slowly expanding the outer envelope of the star. At this point, the size of the star is increasing because of the increasing expanding envelope, which means the luminosity of the star increases as well. On the other hand, the effective temperature drops and the star now becomes a red giant. The temperature of the core goes on increasing until it reaches 100 million Kelvin, when helium begins to fuse into carbon via the triple alpha reaction. At this point, the star becomes hotter but slightly less luminous because the outer envelope is no more expanding but in fact contracts slightly as the star continues its journey through the red giant branch. The point at which helium begins to fuse in low-mass stars sometimes occur with the production of a lot of energy almost instantaneously and is therefore called the helium flash. The Sun is expected to experience a helium flash around 1.2 billion years after it leaves the main sequence. Beyond this point, the Sun is likely to become a white dwarf. White dwarfs are unique in their own right and very much unlike the stars as we know them up to this point. So we'll discuss them in an upcoming video. To wrap it all up, we have explored the fascinating stages of star formation, from those mysterious molecular clouds to the exciting moment when nuclear fusion ignites. Stars are vital in the cosmic cycle. They create the elements that eventually lead to planets and life as we know it. So every time you look up at the night sky, remember that those twinkling lights are a result of an incredible journey. Now, I want to hear from you. Do let me know what fascinated you most about the evolution of low-mass stars, and if you are learning and enjoying our content, please do subscribe to our channel and share our videos with more astronomy enthusiasts. I'll see you next week with a new video on the evolution of stars. Until then, take care.